All right, so this is where we are. We started talking about controllers. We said that we have to build controllers. Okay. Then we said that uh, uh, to start with controllers, we have to express what kind of controller, how we want to build a controller. Okay, so we said tabular methods doesn't really do as an interface for us, and therefore we defined state diagrams. And then we said the state diagrams are easy, but then there may be conditions that we have to go from one state to the other and all that. And therefore we said the front end for our design for a controller is to come up with a state diagram for the transitions and for the behavior of the machine. Then we said, okay, fine, we will do state diagrams. But then the problem with the state diagram is it may get way too complex. So this is what we decided. We said, let's come up with a state machine with a state diagram, which is simple enough that we can represent it easily and discuss it easily, and then we will generalize it to maybe very complex controllers. So we started with a Moore machine. Okay, we started with what is referred to as a Moore machine. We came up with the state diagram of it. Okay, the behavior, the way it was required, we came up with a state diagram like a flowchart. Then we said the next step from state diagram is to do a state table. The next state from the state table is to do transition table. Transition table is where we assign the names of the state. We assign them some binary values, and that becomes transition table. Then we said, well, transition table gives you the next state. I don't want next state. I want a table that I can turn it into Carnot maps. And therefore we said, okay, let's take the pluses out or the next state out and change the transition table to inputs of flip-flops such that with those input I will be able to cause these transitions, these required transitions. Meaning I like the excitation of the flip-flops so that they will be causing these transitions. So we said, let's do excitation table. Then we did, based on the flip-flop we want to be using, we did excitation table. That's close to the Carnot map. So we said, now we have something that we can turn into Carnot map, and this is where we left off. So what I have here is excitation table for the chosen flip-flop D type, D2, D1, D0. This is a, see, one variable, 2, 3, 4 variable, 4, D2, D1, D0. So let's come up with 3 4 variable maps. This one for D2, for D1, for D0. Okay. And then when you look at the output is only a function of V2, V1, and V0. And therefore, that doesn't require a 4 variable map. All it requires is a 3 variable map. Input does not participate here. So what I do is I take the data from the previous table and just put them in these Carnot maps. Let me just do a few of these so that we clarify saying, how things are taken from those tables and put in these tables here. Let's, for example, look at J1, V2, 0, V1, 1, V0, 0. Okay. And let's see 1, 0, 1, 0. Spot 1 0 1 0, what it requires for D2, for D1, and for D0. For D2, D1, D0. 0, 1, 1 in this order. D2, D1, D0. 1 0 1 0. Okay? In this spot for D2, I want 0. In this spot for D1, I want 1. In this spot, same exact spot for D0, I want 1 0 1 1, which is this 0 1 1 goes D2, D1, D0. Okay? I'm actually doing exactly the same thing. Let's box it. Okay. Let me do one more of these. Okay. Let's use this purple one. J0, V2, V1, V0, 0, 1, 1. And therefore I want 0, 1, 0 in D2, D1, D0. So it's 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. Okay? 0, 0, 1, 1. I guess I've done this in the previous part. 0, 1, 0. 0. Okay. 0. 1, 0. So we continue with this, and then we have our table, the Carnot maps all set, and then we do the mapping. Let me do the output. Notice the output is only 1 if V2, V1, V0 is 1, 0, 0, and don't care for the rest of it. Okay, so when V2, V1, V0 is 1, 0, 0, okay, here's a different color. Here. Okay. I put a 1, 1, 0, 0. This is the 1. And doesn't depend on J. So I just put a 1 there, and this becomes W. Based on this, no need to go into Carnot maps, but they're easy. The D2 table becomes fairly easy. There is a 1 here, and then there is a don't care next to it, so this becomes J V1 V0. That's it. For D1, I have essential prime implicand. This is an essential. Actually, the J bar V0 is essential. J bar V2 is essential. Actually, all three of the are essential. And the J V1 V0 bar is essential. Okay, that gives me D1. I'm showing D0. And then finally, I'm showing the output, which becomes as simple as just V2. Okay, what are these? These are the D inputs. And therefore, I build this circuit. This circuit is what is described in these tables. Okay? It is pure combinational. Remember, Carnot maps are for combinational circuits. Okay? And I build those Carnot maps. I build these Carnot maps, and then based on that, I came up with this logic. But then we left off something, remember? We said that back here, We said that these are the transitions. And then to make our life easy, we said, let's forget about transitions. Let's talk about the excitations of the D flip-flops. Okay, what we have come up with are the D inputs. The D inputs are what become the next states after the clock. Remember, Q plus for the D is D. And therefore, now that we have the Ds, we put 3 flip-flops here that the Ds give us the next Vs. The excitations, these are the excitations. These are the transitions. These are the pluses that we had. Those are the before the pluses that we have. What causes the pluses? The flip-flops. And therefore we take the combination logic, put these 3 flip-flops, and then these 3 flip-flops become the next Vs. And therefore, we wire them back into the inputs. Inputs V2, V1, V0. What do we have here? As we expect, a combinational part with a register feeding back into the input. Okay. I haven't shown the output. V2 is the output. And therefore, V2 is the output. Okay, and this is the, what did I name the output? W. How does my circuit look? My circuit looks like this. J, W, 3 state variables, 3 flip-flops, and then feeding back to the inputs. Okay? These are the flip-flops. This is the green area, right? This is the green part. And the register is the blue one. Okay, that's probably the closest I can get to that. All right, that is the implementation of a Moore machine. And let's go through the timing of this Moore machine. Let's give it an input 1 0 1 1. Okay, 0 1 1 1. When I say let's give it an input, and my circuit is a synchronous circuit, which is it, okay, it means, and then the clock is rising edge, it means that 1 0 1 1 0 1 1 1 2 3 4 5 6 7 8 in 8 consecutive edges of the clock. These are the values on the input. And I only look at the edges of the clock. I don't look at the duration of the, and which edge? The rising edge of the flip-flops. Okay? So what I have here is, on this rising edge, the input is 0. On this rising edge, the input is 1. On this rising edge, the input is 0. The input is 1. The input is 1. The input is 0. The input is 1. The input is 1. The input is 1. And therefore, I say that I have seen 1, 0, 1, 1, 0, 1, 1, 1. Okay, let's follow the timing with the state diagram. Initially, I'm in state A. And then I remain in state A when the clock edges. The clock edge is seeing a 0 on the input. See, if I'm in a clock edge, while my input is 0, brings me back to state A. I remain in state A all through after the next edge of the clock. The next edge of the clock is seeing a 1, and therefore I'm going to state B. The next edge of the clock is in state B, and I'm seeing a 0 on the input, therefore I go to state C. I don't change this state until the next edge of the clock. On the next edge of the clock, I have a C and a 1 as input, and therefore I go to state D. In state D, I see a 1 on the input, see, and in state D, I see a 1 on the input, and therefore the next state which changes after the edge of the clock is state E. In state E, what do I see? I see a 0 on the input, and therefore, don't worry about the output yet. Therefore, I see a 0 on the input, therefore the next state becomes state C. In state C, I see a 1. See, in state C, I see a 1, and therefore takes me to state D. Takes me to state D. In state D, I have a 1 on the input. Don't worry about the input that is going 0 and 1 and all that. That doesn't matter. What is important is in state D, I have a 1 on the input on the rising edge of the clock. In state D, with a 1, I go to state E. In state E, with a 1, I go to state, see, with a 1, I go to state B. Okay? What happens to my output? What happens to your output? See, your output becomes 1 when you are in state E. Your output is 1 when you are in state E. Where the places that I am in state E, one is this. After this edge of the clock, clear through the next edge. After the edge of the clock, through the next edge. And therefore, my output becomes 1 coinciding with whenever I'm in state E, which is after the clock, clear through the next edge of the clock. Okay? To be a little bit more color consistent, maybe I want to do this. The output is 1. But then, the same way I look at my input only on the edge of the clock, I look at the input only on the edge of the clock. Look, I'm not looking right here. When I'm in state E, when my input goes to 0, I don't look at it. I ignore it. I say, my input is only important on the edge of the clock. The same way, I look at my output only on the edge of the clock. And therefore, if you ask me, where are the places that the output is 1, I show you the places that I have asterisk on. Okay? Is my output 1 here? I don't really care because it doesn't coincide with the clock. Only here on the edge of the active edge of the clock, that's where my output is important. And this is an important timing that you have to understand. All right, let's continue on and let's do the Verilog description of it. Okay, we have already shown a Verilog description for a sequential circuit described by its state diagram. Okay, and there is a very close correspondence between the state diagram and the Verilog description. Okay, we have said this before, I'm going to say it again. Take the state diagram and look at the transitions. The transitions themselves decide on an always statement that is combinational and that corresponds to going from one state to the other. Then decide on the output value. That itself also gives it an assigned statement or an always statement. And then you have the register transfer. So this is what we have. I have a present state going into my flip-flops. A a present state as the output of the flip-flops, a next state which will be decided by the combinational circuit that are the inputs of the flip-flop. And therefore, I have a register part that takes next state, clocks it into the present state. That's all it does. But then I have a combinational part that I keep calling transition that takes the present state, primary inputs, okay, and decides on the next state. I also have a combinational part that corresponds to the output. That too has the present state, the primary input as input, and then the output becomes the output or the primary output. So this is my W in this example. This is the J input. And then I have to have something for present state and next state. Because I have decided that the PS and NS are going to be given values inside always the statements, and therefore I declare them as reg on line 2. Okay? Before we go to the flip-flop part, let's do the combinational for the transition. Combinational for the transition is this. Corresponds to this dark red thing. Okay? It takes J as input. Notice the sensitivity list. J as input. PS as input. Okay, as soon as it comes in, the output of it is only N state, next state. As soon as you come in, set next state to all zeros on line 6. Then look at the case. The case looks at the present state. And then you will be following state by state as you see things down here. Okay, so 3 tick B0, 0, 0 corresponds to state A down below. So you look up there and then down below. If my J is 1, the next state becomes B, which is 0, 0, 1. Otherwise, the next state is A, which is 0, 0, 0. That's the first line. The next line, which is line 9, but I have to have it to the side. The next one is state B. State B, if J is 1, I'm going to go back to B, and therefore J1, 0, 0, 1. Otherwise, go to 0, 0, 0, 1, 0, which is the state C, and then continue like that. Okay? And then 1, 2, 3, 4, 5, I have a default after that. That means if ever, for any reason, I end up in one of the 3 states that are not specified here, what happens is, well, if noise comes in, if there is a lightning, thunder, or whatever is there, and your circuit ends up in a wrong state after the first clock, when you go into the default state, or default choice of the case statement, then you go to state A. That takes care of the transition, which is the main part of it. And then you have the output, which is this. Notice that the output says, if I'm in the, if my present state, okay, is 1, 0, 0, which is the state E, my output is 1. And this is exactly what I'm saying in this state diagram. So there is a one-to-one correspondence between this Verilog description and this state diagram. Finally, I have this? What does it do? Simple. The next state clocks into the present state. Except that I have an asynchronous reset, and therefore this is how I describe it. On the positive edge of the clock, and when reset is 1, flow begins. If reset is 1, put zeros into the present state, otherwise put next state into the present state. And that corresponds to this exactly. Okay? I've shown you 2 Verilog examples, and both of them follow the same rules. Transitions in the dark red always statement. Output in the dark blue always statement. And then sequential part clocking in the light green always a statement. If my output was more complex than what you are seeing, I would probably use an always statement for that too. Notice when we are back here, notice that I'm taking my W from V2, okay? But then instead of taking V2 from here, I went all the way around and took V2 and took my output from the input V2. The reason is I'm following this model here, that the output is coming from a combinational circuit into which the inputs and the present states contribute. Now, maybe in this particular case, the input is not contributing to the output. In this particular case, only V2 is contributing to the output. Okay? Nevertheless, I take it from the input side. All right, the next part, I do a Mealy machine, which is a different kind of sequence detector, timing-wise.